Okay. Okay, now as you're finishing up writing your names, I want you to identify your colleagues next to you, your neighbors. You're probably already clustered into groups of friends and people you hang out with, right? If not, just gonna try to congregate to the closest person to you. I mean, if you feel uncomfortable, stay within a safe distance. It's up to you. I don't care. But I want you to form a group and come up with a cool name for your group. The cooler your name is, the less likely I will choose you, or the more likely, I don't know. But come up with a funny name for your group, like, the Pythons or whatever, something funny related to numerical methods, okay? And I also want you to write your group's name, put it on a sheet of paper and put it in front of you. Maybe another sheet if you want. Yeah, so I can see your names here, all of you. Yeah, like this is like a perfect group, groups of 2, 3, 4, it's up to you. Maybe Brooke, Kimball, Adam, and 2 to 4. You can be, that's a huge group. You can be 5. No, well, we can't, this is like, okay. So Jake, you okay with these guys? Okay. All right, come up with a group name. Brooke. Okay. You guys, I don't know. Maybe the 3 of you, the 2 of you, perfect. That's fine. That works. The groups will be able to collaborate with each other in the future. Or you're like Googling some funny names. The AA batteries, love it. All right, so we got the first group here, the AA batteries. We got our first group over there. Maybe I'll use the microphone. We got the first group over there. It's called the AA batteries. Come on, guys, come up with funny names. Okay, so I want this back. Is this a AAA? That's a AA. It's a AA. Yeah. It's rechargeable. Okay, group names. Still working on it. All right, while you get working on it, give you a minute. You came up with a group name?
Yeah, Team Kirby.
Team?
Kirby.
Okay. But I cannot read it. If you want to put it on it, I cannot see it. You want to put it on larger, using larger font size. Okay. It's so hard to hear with the masks on and everything, so maybe it's easier to chat. Okay. As you work on your group names, okay, I'm going to continue the lecture. Now, what will happen is the following. When we have a group activity, most of the activities are going to be group activities. So you'll be able to work together to solve the question, the activity. Now, as you work in groups, you will naturally gravitate to someone being the speaker of the group, someone being kind of the scribe of the group, someone being, the devil's advocate, whatever, okay? All sorts of things, right? And that's up to you. It's a fun thing. The more you talk, I want it to be loud, okay? I want you to talk to each other and communicate. because turns out, something interesting happens when you speak loudly. You can get, once you hear your ideas, you'll recognize how good they are or how bad they are, right? So once you speak them out, something happens in your brain and you'll be able to become a better thinker. Okay? So most of the activities are going to be group activities. And I'll give you a couple of minutes, you work on the activity, and then I'll randomly pick a group and see what they have to say. And other groups are allowed to say, no, this doesn't make sense, for example, or we disagree. And they're allowed to give another answer. Okay, so dissent is very healthy in science. Okay. All right. Relative approximate error. That's, I think, where we left off last time. Remember, we talked about errors being important in everything we do, and specifically in numerical methods. We talked about the true error, why it doesn't make sense, and the relative true error. But the true error in general, why it doesn't make sense, except when you're calibrating an instrument or when you're calibrating a numerical method. So you test your technique on a problem for which you know the true answer. If you know the true answer, you don't need to do an approximation, right? So the usefulness of the true error is that it allows you to calibrate your numerical method. So you test it on a problem for which you know the true answer. You check, you make sure all is good and well, and then you move on and take your method or instrument and apply it to new problems for which you don't know the true answer. But in that case, how do you assess any mistakes you've made? So we came up with the concept of the approximate error, which loosely defined is the difference between one measurement compared to a potentially more accurate measurement. How do we know that the other measurement is more accurate? Because we could have tested it on a problem for which we know the true answer. By definition, many numerical methods we develop, because they converge to the true answer, we know that the more terms we add, they're going to be more accurate, as you will see in all of the numerical work we're going to be doing. So it's kind of a given that there is always a method that's a little bit more accurate than the method you're using. So you use that as the truth. You say that the measurement made by the more accurate method or instrument, I'm going to hold that as the truth, and we're going to compare to that one. We spoke about the absolute approximate error, but it didn't give us a sense of scale. So by analogy, we're going to define a relative approximate error, and we're going to say that it's just simply the approximate error, which is the current approximation minus previous approximation, or the low order approximation minus the low accuracy minus the high accuracy approximation, divided by the high accuracy approximation. You notice when we're measuring relative errors, the denominator is always the value that's closer to the truth. It's either the true value or the value that is more accurate. Okay? Now we kind of went over that over Zoom very quickly. Typically, we report relative errors as percentages. We take the absolute value. Most cases, you don't care about the sign of the error. It's not a mistake to report an error with a sign. It's okay. But typically, you be the judge of that. I always report errors if the sign doesn't matter. I always report them as an absolute value. Okay. And we gave the example of this activity. We did it over Zoom the other day, and gave us. Well, actually, I don't think we did this one over Zoom, but we're going to do a similar one in a minute. Okay, so that's taking the Taylor series of the exponential. We did it for the absolute approximate error. It's just repeating the same thing over here with the relative approximate error. So by increasing the number of terms. So I forgot to say that approximate errors, they're useful in many situations, and specifically when we're calculating like Taylor series and successive approximations where you can add more and more terms. It allows you to identify when you can stop adding terms in an approximation, okay? So in this case, this is what your calculator is doing. When you grab your phone or your good old-fashioned calculator, you start punching numbers in it to calculate the exponential. Internally, that's what your calculator is doing, because This symbol e to the x, how do you calculate that? That's, Siri is having trouble hearing me. Okay, so, you know, your calculator is doing this Taylor series, okay, because calculators know essentially what we can basically do is multiply, divide, and subtract and add, right? So on the right-hand side, this is just simple algebra, right? So the exponential is written as this form, but when do you stop? Like, when is a good measure? How many terms do you need when you're doing a calculation? So internally, your calculator has a preset tolerance, says, I'm going to calculate the exponential until you reach a relative approximate error of 1%. Okay, so it keeps adding numbers until you hit that. It could be that e to the power 0.1, you can reach a tolerance of 1% by using 5 terms, but e to the power 15, you might need 50 terms for that. Okay, who knows, right? So that's kind of a nice mechanism. Now we're going to use the approximate error for more advanced things, but anyway, this is kind of one way to use it. Okay, so this is going to be your first activity as a group now. I want you to go and download the following Jupyter notebook from the errors module in Canvas. So if you go on Canvas, on your left-hand side, there's a menu, right? There's one menu item called modules. And you go under modules. The first module we're covering these days is errors. And there's a couple of Jupyter notebooks over there. So go ahead and download that Jupyter notebook. So let me see, I can show you how it looks like. Gotta turn this way. So if you go over here, you see under modules, you see errors, and there's this one called Taylor series relative error with gaps .ipynb. So ipynb stands for IPython notebook. That's before it was called Jupyter notebook. It used to be called IPython notebook. Okay, so download that. Actually, download both of them if you want. And just, if you're running Jupyter locally, then ramp up your Jupyter notebook. If not, go on the CHPC website and upload this to your CHPC website. If I can. This hopefully is a little bit better. Okay. Please don't fall asleep. Okay, so the question is, you want to write a Python code that uses the Taylor series to evaluate the exponential function down to an error or tolerance of 1%. So a relative approximate error of 1%, okay? Recall that this is the formula for e to the x, so this is what you will be doing. So we're going to be adding terms. We're going to keep adding terms. Every term we add, just like we did on the previous slide and the last activity last week, we're going to measure the error. Okay, for each term we add, we measure the approximate error until we hit 1%. When we hit 1%, say, good job. Okay, now this notebook, Taylor series relative error with gaps, has already some code in it. Okay, and we're going to work with that code and you're going to be filling in the gaps. All right, if you're all set, let me open up that notebook if I can find my cursor. Fonda. So I run my local Jupyter. Okay. All right. is if you have that open, this is what you should be seeing. Folks on Zoom, are you okay? Are you seeing this?
Yes.
Thank you, Matthew. Okay, let's see who's got that up and running. All right, you guys are way ahead of me. Perfect. Okay, so I'll guide you through the first few steps and then we'll start the activity, okay? So, you know, you got the description here of the problem and I'm importing the math library because I need the exponential function. Now, this is a problem where we know the true value, okay? And just for kicks, I'm gonna use the exponential function just if I need to compare my approximate value to the true value. But also I'm gonna need the factorial, right? So you see over here, you have 1 plus x plus 1 over 2 factorial x squared, etc. So I need access to the factorial function, and that's provided by the math module from Python, okay? Now, if you're new to programming, you might use Python as a calculator. Essentially, you might go ahead and start writing each term in and of itself and computing the error for each term and kind of do it by hand using what I call the brute force approach. So you would start by declaring a variable x, you put the value 2 in it because we're evaluating e to the 2, okay? Or whatever value we're evaluating the exponential really, but at whatever x value we want. And the exact value is defined as math exponential x. The first term in the Taylor series is 1, and the first result essentially is term 1. Term 2 is x, and our second result is 1 plus x, right? So that would be the first 2 terms, 1 plus x. And then you would calculate an error over here, which is result 2, which is 1 plus x minus 1, right? Over result 2, which is 1 plus x times 100. So in other words, you could say, you know, over here, you could probably say this is 1 plus x. Well, not probably. You could definitely say this is 1 plus x, okay? And then result 3 is simply equal to 1 plus x squared over 2, okay? And then the error would be result 3 minus result 2 over result 3, right? So that's a current approximation minus previous approximation over current approximation, right? So result 3 is the current approximation or the higher quality one minus the previous approximation over the higher quality approximation. Okay, and then I'm printing the error, and you do this all the way, okay? So if I run this cell, let me import math, and I can go and run this cell, this is what I get. For the first 2 terms, so 1 plus x, I get an error of 66%, which is what we got on the slides, right? So we agree with that, that's good. Okay, then 40%, 21%, 9.5%, okay, and so on. Now, that's, you know, if you've done some programming, that's really bad use of a powerful programming language. That's using Python as a calculator. So it's really not using Python at all, okay? But it's okay to do that if you're playing around, getting started programming, you know, definitely do that. See that this is fun and interesting and it does produce something, okay? Now, what we want to do is we're gonna go ahead and do a for loop. Now, I'm assuming that most of you, based on how many hands were raised last time, you know how to do a for loop, okay? So I'm gonna go over this a little bit faster. So instead of doing these terms, result 1, result 2, result 3, result 4, we can automate this process because we know the formula. It's the summation, you know, x to the power n over n factorial. So we can add as many terms as we want with just simply a template with a for loop. So we're gonna do this with a for loop. What I'm saying here is probably something, I hope it has some wisdom in it. Let's see. In a for loop, you can do a repetitive calculation for a specified number of times. And we typically use the Python range function to create a counter that automatically increments, okay? The range function takes 2 arguments, a start argument, so where do you want to start counting from, and a stop argument, where do you want to stop? So why is this useful? Let's say you want to add 10 terms together, right? You want to tell Python, I want to add 10 terms. How do you do that? You create a range from 0 to 9 or from 1 to 10. Okay, so it's just a counter that allows you to do that. Okay, so you can try this for I in range 0 to 10. So that was explained also in the slides, the Python slides, which I hope, well, I got many homework submissions, so I'm guessing most of you did it. So if you do this, this is what it prints for you. It just prints a count number, okay? And if you omit the 0, so range starts at 0 and goes to 10 minus 1, okay? So it gives you 10 values in total from 0 to 9. And if you omit the 0, because it's just easier, it defaults to 0. So if you print I in range 10, it's just gonna start at 0 and go all the way to 9, okay? All right, so now let's see how we're gonna do this for the Taylor series, and this is where you're gonna get ready for your activity. So when you're thinking about a problem like this, and I'm gonna guide you through these first few problems as we start thinking how we're gonna Pythonify these math problems. So what do we need for this Taylor series to work? Okay, what do we need for these Taylor series to work? If you want to take a moment and think about this individually, what would you need to make this Taylor series work? I'm kind of giving you the answers over here, right? So, you know, we would need a value x for which we want to calculate the exponential, right? That's e to the power 5, e to the power 0.1, correct? Okay. But for this for loop to work, we need a variable in which to store our result, right? Because each term we add is going to contribute to the answer, right? E to the x could be equal to 1, or 1 plus x, or 1 plus x squared over 2. So each one of those, every term we add, we need to store this somewhere. So I always like to call my answers result, so that I know it's the result, right? That's my variable called result. I can call it, you know, NWP65, but that's useless, right? So result is the name of my variable I want to call. And we also want to define the number of terms we want to do in a Taylor series calculation. And I call this n terms, okay? And we need a factorial function to do n factorial. So how did I think about this? Here's one bulletproof way, okay? This is the Kevlar vest of programming, okay? For each problem, your code, think of your code as a black box. You only know what's inside that black box, but think of it as a box that takes input and produces output. And then ask yourself, what do I need for my black box to operate? What are the inputs, in other words? And what do I want my black box to produce? So in this case, we need the x value for the exponential, the x value, the value that we want to exponentiate, and we need the number of terms. So how many terms are we going to carry in this Taylor series, right? And as output, we're going to produce the result and potentially an error as well. Agreed? Okay. So now go ahead and just the first thing we want to do before we hit the error tolerance, I want you as groups to fill in these gaps. And I gave you a skeleton code over here to start by defining the x value. I define a variable called result. I put question marks here for you to fill in, okay? Work as groups, okay? N terms equal 10, and then this is where you're gonna put in your formula, okay? So go ahead, work as groups, okay? Start programming. I'm gonna walk around. Feel free to ask me questions as I walk around, okay? Just try something. If this is like, whoa, this is all new to me, try something, okay? Try something. All right, get going.
And then
Good thinking, good thinking. You okay working by yourself, Jake? Okay, perfect. Okay.
And to be my last, it doesn't matter.
Working groups, please. If you don't know each other, introduce yourselves to each other. Get working in groups, okay? Are you guys, you wanna, yeah, gang up as group, good, good.
My only question is for the Henry. So
Yes.
end terms in the 10th.
Mhm. So here's what you do. There's a, if you are in doubt, print it out.
Okay.
So go and print like for I in range 10, right? See what it does for you. And then, count those numbers, right?
My only issue is that the print exact val won't work.
Oh, because we did not define exact value. Oh,
Which is
comment it out.
That's what I
Yeah,
did. And then I
comment
just
it out.
printed the result.
Yeah.
Okay.
So you probably have an older version. So you see over there, exact val is math.extx.
Oh, because I'm down.
Did you download the recent version?
I have the recent one. I just pulled it
This
off.
is the most recent one?
I thought
Yeah.
so. I did
Okay.
like
So
three,
let me see.
four,
Go down, go down.
3, 4, 5. We're in line, and then mine just goes to line 9,
Oh,
and then 7, and then 8.
okay. So go up, Yeah.
Right?
Yeah, that's the one you just filled out.
Yep.
That's weird because I just downloaded this from the. Yeah,
Well, maybe
right.
Maybe I downloaded this like last week.
Pardon me.
I think I downloaded this last week or something.
Okay.
But that's
All right.
fine.
I apologize for this. I might not have updated it, but
Oh,
yeah. So it's just
that's fine.
math.txt. Okay. Okay. So pay attention to this. You might get, and this might be missing from your notebooks, the exact value. Okay. All right. Need a little more time. I love your group name. All right, time. Let's call it time. Let's see. Do we have a group who's got some answers? I know a couple of groups already had this nailed down. Okay, what's your group name? Oh, did you raise your hand? Sorry, Kevin. Oh, all right. So who would like to let us know how they thought about this problem? Go ahead.
We started with the results.
Okay, why? Right? And why 0? Why not 1?
Because we don't have any terms yet. I don't know.
Okay, Tata. Right, exactly. Yes. So you're right to choose 0 because we're going to be adding to that quantity, right? This is an additive series. If we were multiplying, we would probably start with 1, right? So that you don't mess up that initial kind of value. Okay, great. So we got 0.0 over here. I always like to put a decimal point to enforce the idea that I'm dealing with a floating. Yeah. Pardon me. Sorry, I didn't hear you.
Would it still work if I do an empty set instead of 0?
No, it will not because this is a result. It needs to have a value in it, right? I mean, Python might do something, it might allow you to do it. I don't know what it might default to. It might default to 0 but I wouldn't bet on that. So I wouldn't be ambiguous, okay? So what Paula is saying is that what if you put a bracket over here, like an empty value, you know, which is technically just a list in Python. I wouldn't do that because this is, I don't know what Python is gonna default this to. On your computer might be different than my computer. So don't be ambiguous about it. Result is a scalar value, a single value quantity, and it is 0. So just put it 0, and I would always put a decimal point to enforce the idea that this is a floating point number, not an integer. I don't want to allow Python to make any assumptions on my behalf, okay? This is my code. Okay, so this is a floating point number, 0.0, okay? So you notice here, every time when I'm not dealing with integers, I put a decimal point. It's a good practice. All right, so, okay, thank you, Jake. Do you guys have a group name? Let's see, Jupiter Snakes. Love it, thank you. All right, who wants to take on the range question? Which group would like to take on the range question? Oh, yes, go ahead. And terms, okay. So we just put in here and terms. Now why? We said we want to add 10 terms, right? And based on what we know about the range function, what we just defined, range goes from 0 to n terms minus 1, but it gives you n terms because to count from 0 to 9, that's 10 entries, right? So whatever n terms is, you put n terms over here, this is gonna do the right count. Now, what I just told your colleague just a minute ago, and what I say in every lecture, in every programming lecture in this class is, when you are in doubt, print it out, okay? When you're in doubt, print it out. Okay, so you don't know, you forgot what the heck range returns. Just create a new cell and print it. Oh, I forgot what range does. Okay, so I'm just gonna do for I in range 12. Print I. Oh, it gave me, it started from 0 to went to 11, but those are 12 entries, right? So the number you put in that range function is the number of times that loop is gonna execute. So we need 10 terms, just put 10. If you forget, just print it out. Again, repeat with me in your heart or loud. When you're in doubt, print it out, okay? It's a very easy thing you can do. All right. Let's get rid of this cell. Okay, so n terms. Now result. Okay, who would like to help with the result? Okay. Well, I know a couple of groups in the back there who have the answer. Go ahead.
We got results plus 1 over math factorial of n
Okay.
times x to the n.
Okay. Result. Let's see. So guide me through it, will you? Result is equal result plus.
1
Okay, I'm going to put 1.0. Okay.
over math factorial
Math dot factorial of n. Okay.
times x
X to the power n. Okay, anyone disagrees with this formula? We agree it's a beautiful formula and it's right. Okay, thank you. Now, Kia, do you want to explain why? What does this mean? Result equal result.
So it's basically just using the Taylor series formula because in the formula it still has the x in there. So that is like saying that you want to use your x plus
whatever terms you accumulated before. Okay, so do not interpret this as a mathematical, in the true mathematical sense. So in math, when you write x equal x plus 1, that doesn't make sense, right? Because you cancel out the x's. In programming, that's not the equivalent of math. In programming, what this is saying, it's saying the new value of result. So this variable has not been assigned yet, or the new, what I'm gonna put in the memory of this variable, I'm gonna put whatever existed already plus something. So the new value of result is equal to the old value of result plus something. That's how you should interpret this in programming. Now think this through. The first time we enter this loop, okay, n is going to be 0, correct? And the result is going to be 0, correct? That's when we came in. So the new result is going to be the old result, which is 0, plus 1 over 0 factorial, which is 1, times x to the power 0, which is 1. So now your new result is 1. Now the loop increments. N is equal to 1 right now. Result has the value 1, correct? Now we say the new result is equal to the old result, which is 1, plus 1 over, what is n now? 1. So 1 factorial is 1, times x to the power n, which is 1 times x. So you change your result, it became 1 plus something, and then you continue. Now this is typically one of the first barriers when you're thinking about programming, because you tend to interpret this as a mathematical formula, x equal x plus something. That's wrong. That's not the interpretation. This is saying new value is equal to old value or existing value plus something. Programmatically, what the computer is doing, result is only referring to a location in memory. Okay, and it's saying, I want to update whatever is in that memory with whatever existed in it plus something. Okay, all right, so let's execute. Look at that. So with 10 terms, our approximate value was 7.3887, etc. But the exact value, or the value that I obtained from the built-in Python routines, is 7.390, etc. Now you can play with this. You can add more terms. You can do, 20 terms, and you see how close we are getting, right? So this is what we computed, and this is what Python computed. So now we know how to do a Taylor series, okay? Now let's take it up a notch. Now I want to calculate the relative approximate error for each term in the for loop. So I want you to do essentially what we've done on the slide. For each term, I want you to find the relative approximate error. Okay, and this is the skeleton of the code. Now, there's a little challenge over here, because to compute the error, you need to store the old result, right? You need the previous approximation. Okay, so what I did here is I made a copy of the previous approximation and I called it old result. Okay, so what I have here, x equal 2, result equals 0.0, and terms equal 10 for n in range, and terms, and then I have the result over here. Okay, but now you have old result and the error. Okay, go ahead. Remember, the relative approximate error is current approximation minus previous approximation over current approximation times 100.
Oh, I was just curious on this last part right here. Is this what?
Yeah, no, we're not going. You're way ahead of everyone. Yeah. No, that's no. But I'd rather you guys work together so that you just do it. Looks like you're way ahead, so that's great. So you can scroll down to the cells below and you can copy the formula. That's not going to help you a lot, okay? Error less, is that your group name? Cool. Okay. All right. Let's see. Okay, let's call it time. The batteries, you guys have an answer? That's okay. It's, you know, it's okay if you don't have an answer. Okay, let's see. Who would like to help pitch in? Who would like to pitch in? Yeah, go ahead. Yeah, why? Yeah. Yeah, we got to keep changing that previous result that we have. We got to keep using that as our previous approximation. So I'm going to store the value of result in, if I can find my cursor, okay? So I create a new variable called old result in which I'm going to store my old result because I need a hard copy of it. Okay, I need a copy of it so that I can use it to calculate the approximate error. And I need to put this before I compute the new result, right? Because when we come into the loop, all we have is the old result, correct? So we grab it, we make a copy of it, we put it in old result, take a breath, you know, and then compute the new result. Now we can compute the error. Who would like to give me the error? I mean, go ahead.
So the error equals absolute result minus old result
Times 100. Excellent. Okay. So what we got here is absolute value of old result minus result over result. Okay. Oops. Over result. So low accuracy approximation minus high accuracy approximation over high accuracy approximation. Okay. In absolute value, it doesn't matter the order how you take them. Okay. Times 100. Let's run this guy. Aha. Gorgeous. Yes. With an absolute value, it doesn't matter. Well, but if you want a signed value, you would probably do new high order minus low order. Okay. Now, in the end, it doesn't matter because let's assume you're writing a report about something and you say, okay, I'm going to define my approximate error as this. And then the interpretation, if it's negative or positive, would be based on whatever definition you make. Okay. So it really doesn't matter. Okay. And yeah, I'm not going to judge you on it. Okay. So that's the least of my concerns. Okay. Now this is cool because now for term 0, the zeroth term, there's 100% error because we don't know any better, right? We don't have any other value to compare this to. Okay. For the first term, 66%, 40%, 21, 9, 3, 1, 0.4, right? Okay, that's good. That's really great. Okay. So within 6 terms, we reduce the error to 1%, okay? So now the next step is to tell Python, to tell our code, stop there. Because if we were to choose a different number, so let's say we do 0.1, what? 0.1, okay. 0.1, look at that. You hit 1% within 3 terms, right? So the number of terms you need to get to your tolerance is going to depend on the value of x. So you really don't want to specify the number of terms. I would specify a large number of terms and tell it to stop internally. Once it hits whatever tolerance I want, then I want it to stop computing. Otherwise, it's just wasted effort, okay? So you can try, if you want to do the exponential of 20, if I can type well. Look at that, a lot of errors. You probably need a lot more terms when you're exponentiating large values. You need a lot more terms to converge it, okay? 10 terms is not going to be enough. So that's the next step, and probably the final step that we want to do in this is that, how do we tell it to stop? We need an if statement, okay? You want to take a minute to fill this in? So n terms, I don't know why I still have question marks over here. So I'll just put, actually, no, I do have a question mark over here. N terms is a question mark, and I want you to put in an if statement here to tell the code, once you hit an error of 1% or less, stop, okay? So that's what this break does. It says break the loop, okay? So go ahead, you got 2 gaps to fill in, the number of terms and the if statement, okay? Okay, to the folks on Zoom, I'm hoping you're able to follow through. I'm sorry, you haven't been as engaged in the activities as everyone here in class is, but I'm hoping you're following up with us. Let me know. I can hear you through my earphone.
Yes, I think that's going well for me anyway.
All right, thank you so much for the feedback. I'm gonna take my battery back. I forgot to charge it, so I had to use this earphone. It's hard for me to hear with the earphone, so compared to the other headset. Soup. Soup. You guys are nodding in agreement. Looks like you have an agreeable answer. Okay, let's see who's got an answer. Preferably a group who did not contribute earlier. Go ahead, Paula.
So n terms, I just did
50.
50.
Okay. Why?
I just did a big one.
Just a,
One of those-
you think 50 is a large number?
Yeah.
Okay. Why not 1 million? Right. So what do you think? What should we, I mean, I think you're right to put a number there, any number, but it has to be large. So I understand why you think 50 is large, but in these things, I'll probably put like 1 million or 10 million. Okay, because we're never going to hit that, hopefully. Okay, we're never going to hit that, because if our code is right, it's going to stop where it needs to stop. Now on the flip side, maybe 50 is not a bad idea. So like I'm playing devil's advocate with myself. So maybe 50 is not a bad idea, because I don't want this thing to keep computing forever, right? So maybe 50 or 100, would be a good idea. And it would be saying essentially, you know what? If you don't get an answer to a tolerance of 1% within 100 terms, I don't want you to continue consuming my resources, okay? So really, it's up to you to put that number, but bear in mind the implications. If you're exponentiating a value that is going to that might require 2,000 terms to converge to 1% relative error, then 50 terms is not going to cut it, or 100 terms is not going to cut it, okay? But understand that that's the limitation of your code. One way you could test is run your code on a range of numbers and say that, you know what, this code with these 50 terms works really well when I'm exponentiating values from 0 all the way to 21.3, something like that, right? Because then you would be sure that you converge within 50 terms, but other than that, I wouldn't use the code, or you need to increase the number of terms, okay? So let's go with what Paula said and put 50, all right? And the if statement is just a syntax over here, right? So what we've done here is the same thing. We've computed the relative error, and now we're going to check if the relative error is less than or equal to 1%. Okay, we're going to stop. Okay, so what's the code there? No one's got the code. Go ahead. To 1%.
And then did if our error is less
If your error is less than that, okay. Less than or equal to 1%. Yeah. Perfect. Okay. So let me see. This is 50 over here. Okay. Okay. So tolerance, put it 1 as was requested. And then if your error is simply less than tolerance, or you can put less than or equal, or less than tolerance, then break. And look at that. It took 7 terms to get to this tolerance of 1%. Actual error is 0.344. Okay. So now you can play around with this. You could do, a value of 1, takes 5 terms. You'll notice that the smaller the value, the less terms it's going to take. Okay, took 2 terms to do exponential of 0.1. But if you go to larger values, you're going to need more terms, because the exponential is an exponential, right? It just explodes to infinity very quickly. And then in that Taylor series, you're successively taking powers of large numbers, 50 squared, 50 cubed, 50 to the power 4. It tends to blow up very quickly. And that messes up with the tolerance and the errors, okay? So the higher the value, okay, of the exponential, of the exponent, the more terms you're gonna need, okay? So let's go exponential 10, 18 terms to converge, exponential 30, 42 terms to converge, okay? So we're gonna hit that barrier of the 50 terms. So let's do exponential 50, oh, look at that, 49 terms. But look at the exponential of 50. It's 2.49 to the power 21. That's like an indigestible number, right? So if we do x equal 60, okay. So we actually, sorry. So we are actually, our error is so high. We're not reaching 1%. So we need many, many more terms to reach 1%. Okay. Now an alternative in this notebook for you to stew on if you want. Sometimes you don't want to put a maximum number of terms and put an if statement in a loop. Actually, you want to avoid putting if statements in a loop, because once a code goes into a loop, you don't want to stop it. It's like you're running on a treadmill and like someone gives you like a bottle of water or something. Like you don't want to stop. You want to keep running, right? So that for loop should not be broken. Okay, so you don't put an if statement in a for loop. But how do you have a for loop with a condition? you use what's called a while loop. And that was explained also in the slides. And essentially what the while loop does, it uses a condition, it uses any value inside, any value that you're updating, any variable that you're using, and creates a condition in a for loop. So here what I'm saying, as long as my error is greater than my tolerance, continue adding terms. What happens once the error is below the tolerance, it will exit by itself automatically. So you don't have to worry about number of terms. You don't have to worry about putting an if statement. This is a very efficient way of doing a for loop with a condition. Okay, so you can run this and kind of just stew on it. Oh, well, X. Let me see. Probably made a mistake over here somewhere. Okay. Right, let's see what I went wrong. Okay, x to the power n, and n is 0, while error is greater than our tolerance. Tolerance result 1 factorial. Okay, there you go. I don't know why it freaked out earlier. So this will automatically just calculate the error for you and print the number of terms and the error without having to put an if statement. Okay. All right. Let's switch back to the lecture and hopefully just finish up with errors today. Okay. All right. Okay. So this is a summary of these errors. We talked about true error, okay, and approximate error. True error is used essentially for calibration of numerical methods. Approximate error is used in practice to get a sense of how your numerical method is doing. Okay, I hope to finish this next set of slides. So this is more of a survey on the sources of error. So there are numerous types of sources of errors that we can deal with as engineers. There's the modeling error. For example, you assume the wrong model for a problem you're solving. You know, you're studying how you're going to skydive, you know, in Moab, and you want to understand the drag forces on you and, you know, how fast you're going to be going, etc. But you assume the wrong drag model. You know, that's a modeling error. You've used the wrong, inappropriate model for the, you know, like you looked at the drag over a sphere versus, you know, our complex bodies, right? Programming error, mistaken code. That's, you know, the Ariane 5 rocket disaster, which is a human error too. And then finally, numerical errors, which are our main concern here. And I list 3 primary errors we deal with. Those are round-off errors. That's the inability of a computer to store arbitrarily large numbers, right? So what it does, it just chop them off. We call that round-off error. That's what happened with the Ariane 5 rocket. There's other disasters as well, unfortunately, due to that. Truncation errors, which we will also talk about, those take a full mathematical formula and say, we can't implement the full math formula. So we're going to implement only a piece of it. One example of that is what we just did, the Taylor series. The Taylor series has an infinite number of terms in it, right? Goes to infinity. But there's no practical way we can add an infinite number of terms. So we say we're going to stop at 50 terms or 10 terms. Whatever we cut out, that's an error, that's the truncation error, okay? And finally, iteration error. This is going to be vague a little bit right now, but once we get to iterative solvers, you'll understand what it means. But in a nutshell, it's many methods we're going to learn are iterative in nature. They start with a guess of the true solution, and they refine the guess to get better and better and better to the closer to the answer. The distance between your guess or your refined guess and the true answer, that's called iteration error. Okay. And it's strictly limited to iterative methods, okay? The Taylor series is not an iterative method, okay? It's not an iterative method. It's an example where you have truncation error, okay? Not iterative error, okay? Because it doesn't depend on the initial guess you're starting. All right, let's talk about round-off errors, and this is gonna rough representation of how numbers look like on computers. So think of the different digits as in a number as occupying a spot in memory. That's not how it is in real life. Real life numbers are represented as binary, and these binary states, 0 or 1, are stored in a computer, but still the imagery is similar. Imagine you have a number 0.15464, etc. And you're storing each, you have bins in your computer, and you store each digit as a bin, in a bin. Clearly, the more bins you have, the more significant figures you can store. All right? Now, because the way we build computers, you know, imagine like 20 years ago, I used to, like, my first computer had like 2 kilobytes of memory or something. It was just hilarious. Like, I giggle at that right now. I need at least 128 gigabytes of memory in my computers right now. It's crazy, right? So now, the number of bits, there's typically, in what you find in computers, 16, 32, 64, 128 bits, 256, and so on, because they're powers of 2, really. That's what this is. Now, what happens when you have less bits or less bins than you can use, then you can represent the number. So if the number is larger than the number, let me correct myself. If the number of significant digits in a number is more than the number of bins you have to represent that number, what do? Well, you know, computers, what they do, they just round it. They either eliminate the numbers that they cannot fit in the bins, or can I do some rounding, round up or round down, okay? Now this is called, when you do this is called round-off error. When you have more significant digits than there are bits to represent the number. Here's the definition. Round-off error is the result of the inability of computers to represent all significant digits in a number. It's therefore the difference between the actual value of a number and its rounded representation, okay? Clearly, the more bits you have, the more significant digits you can represent, but they come at a cost because they take up more memory, okay? Now, some of the common floating point number representations that real computers use are 16-bit float. So you have 16 bins per se, 32 bins, 64, 128. This is called half precision. This is called single precision. This is called double precision. And this is called quadruple precision, okay? Python defaults to 64-bit floats for double precision. You have a lot of significant digits that you can represent using Python, which is pretty cool, okay? Now, in reality, you know, everything is converted to binary and you just store the binary digits, okay? We don't have time for this activity, but this is a really cool exercise that you should do with the Jupyter Notebook, the other Jupyter Notebook you download. It's very, very easy. What I want you to do in this activity, if you ended up doing it, is I want you to sum up the number 10 to the minus 5 100,000 times. Now, 10 to the minus 5 is a number that you can represent using half precision, single precision, double precision, and quadruple precision, okay, even higher if you want, okay? Now, it turns out that, well, the exact value analytically is 100,000 times 10 to the minus 5 is equal to 1 exact, okay? Now, 10 to the minus 5, when you convert it to binary, has an infinite number of digits, okay? So we're gonna have to round it. The computer is gonna have to round it, definitely is gonna have to round it. Now, with Python, what I do, I declare there's a way to represent numbers as different precisions. And, you know, we're not going to use that at all. This is just for the sake of illustration. But if you use the NumPy library, it has float 16, float 32, float 64, float 128. NP float 16, 10 to the minus 5 gives you the 16-bit representation of 10 to the minus 5. And I call that x half. That's the half precision representation of 10 to the minus 5. Same thing for single precision. Float 32, float 64 is double precision, and float 128 is the 128-bit representation of 10 to the minus 5. So what happens when you do this? Something really interesting. Okay, you go and do the summation, you add it up 100,000 times. Okay, so you take x half and add it x half, x half, x half 100,000 times, x double, x single, and x quadruple. What you get is, you don't get one. You never get one exactly. You get an error. So for the half precision, your error is 0.14%. So you missed the exact number 1 by 0.14%. Now, once you go to double precision, it gets so much better. 2.5 times 10 to the minus 6, you get to the double precision, goes 10 to the minus 10, and the quadruple precision 10 to the minus 13 error. Okay, so that's kind of always, interesting exercise to realize that the numbers you're dealing with, they're never exact. They're always rounded, okay? So there's a lot of issues for round-off errors in real life. One of them is the Ariane 5 example. Another one is the Patriot missile crisis. I don't know if anyone's heard of that. So the Patriot missile was a very popular air missile defense system that the US military came up with in the 80s, 70s, 80s, and was used across the world to defend US Air Force base, US military bases, okay, from incoming air missiles. So, like Scud, rockets, etc. So during the Iraq conflict, and I actually come from the area over there. And so, this is in my collective memory. I think I was like 5 or something. I don't remember. But so on February 25, 1991, so this is taken from Wikipedia, an Iraqi Scud missile. So the Iraqi Scud is one big ballistic missile, very nasty missile, hit the barracks in Dhahran in Saudi Arabia and killed 28 soldiers from the US Army. And the government investigation revealed that, so this Patriot missile system, what it does, it essentially keeps track of the sky. It has a bunch of radars, keeps track of the sky. When it detects something flying, first it eliminates if it's a bat or a bird, or an eagle, right? And then identifies if it's a fast-moving large object that is incoming. Okay, so it tries to detect, to identify to measure its speed and distance. Because once you know that information, you can predict where that missile is going to go next, and you can shoot it down, okay? So what happens, let's read. The government investigation revealed that the failed intercept at Dhahran had been caused by a software error in the system's handling timestamp. The Patriot missile battery had been in operation for 100 hours, by which time the system's internal clock had drifted only by 1/3 of a second. Now, this was done because of round-off error again. They were translating 16-bit to 48-bit, 48-bit to 16-bit precision. And, that's not a big deal when you're like doing, when you run the system for like, 10 seconds or an hour, but it's been running for 100 hours. So that error accumulated to 1/3 of a second. And now take that 1/3 of a second and multiply it by a supersonic rocket. That's going to be, a distance of probably 200, 300 meters difference in error in trying to shoot it. So it was not able to intercept it at all. Okay. So the radar system had successfully detected the Scud and predicted where to look for it next. However, the timestamp of the two radar pulses being compared were converted to floating point differently, one correctly, and the other introducing an error proportional to the time of operation caused by the truncation in a 24-bit fixed point register. As a result, the difference between the pulses was wrong, and the system looked in the wrong part of the sky and found no target. With no target, the initial detection was assumed to be spurious, and no interception was attempted. It was a huge investigation, a lot of papers written about it, and so about the importance of round-off errors. So round-off errors are a big deal. So make sure when you are working with numbers on a computer, you are clear whether you're working with integers or double precision floating point numbers, you should know so with Python, you're always double precision. So trust that and rely on that, okay? There are many other disasters. The Ariane 5 we talked about last time, the Vancouver Stock Exchange, yeah, it lost, it dropped by 500% in the index because they missed the index with 3 decimal points, producing a drop in stocks 500 points. Very weird stuff. There's a website that tracks all of these round of errors in the modern world. Now, before you leave, I don't want you to worry, okay? So for the vast majority, like 99, like, you know, that number they put on the hand sanitizer, 99.999% of cases, you know, this is not an issue. Mechanical and chemical engineering systems tend to self-correct any sort of errors like this. Typically, these round of errors show up when it's like a post-processing step in a calculation, okay? But the mechanics of like doing, you know, Taylor series, etc., it's usually not an issue. So don't worry about it. Modern computing systems, even if you make a round off mistake, it is so insignificant because we have so many bits to deal with right now. So what if you convert from 64-bit to 32 bits? Yeah, it's not gonna be a big deal. It's still gonna be a mistake, but it's not gonna be a disaster, okay? But don't do that error, okay? All right, so I will see you on Thursday, all right? We have an exam on Thursday. Please watch the announcement. It's a pretty short exam, okay? Bye.